A quiet revolution is brewing in the world of cosmology. For nearly a century, our understanding of the universe has been built on a foundational idea that it is expanding uniformly, like the surface of a perfectly inflating balloon. This concept, known as the cosmological principle, suggests that on the grandest of scales, the cosmos is the same everywhere and in every direction. There are no special places, no unique vantage points, and certainly no preferred axis of orientation. But new evidence, meticulously gathered and analyzed by a powerful artificial intelligence, hints that this fundamental assumption might be wrong. The universe, it seems, might be spinning. This startling possibility comes from the work of Valery Makarov, an astronomer at the United States Naval Observatory. His research, focused on the movements of the most distant objects we can observe, has uncovered a subtle, large-scale pattern that defies conventional explanation. To understand the significance of this finding, we must first appreciate the standard model of cosmology. It begins with the Big Bang, an event that sent all matter and energy hurtling outwards. The most common analogy is that of raisins in a loaf of baking bread. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be receding. This is precisely what we observe in our universe. Distant galaxies are moving away from us, and the farther away they are, the faster they appear to recede. This is the essence of cosmic expansion. The cosmological principle takes this one step further, stating that the universe is not only expanding, but is also homogeneous and isotropic. Homogeneity means that its properties, like the average density of galaxies, are the same everywhere. Isotropy means it looks the same in every direction. Together, these principles imply that the universe cannot have an overall rotation. A spinning cosmos would have a defined axis, a special direction around which everything turns, which would violate the principle of isotropy.
It is this cornerstone of modern physics that Makarov's work now calls into question. He developed a sophisticated machine learning system, a form of artificial intelligence, and trained it to become an expert in measuring cosmic distances. To do this, he fed the AI data on 280,000 quasars, which are the intensely bright cores of distant galaxies powered by supermassive black holes. Their distances had been previously and painstakingly calculated, providing a reliable training set. Once trained, the AI was let loose on a colossal dataset of images from two of our most powerful space observatories, the Gaia satellite, which maps the positions and movements of stars with unprecedented accuracy, and the WISE infrared telescope, which can peer through cosmic dust to see the faint glow of faraway objects. The AI analyzed the positions and movements of an incredible 1.57 billion objects. These weren't nearby stars. They were ancient galaxies and quasars located between 7.7 and 11.5 billion light-years from Earth.
If the standard model were perfectly correct, the motions of these billions of objects, once the general expansion was accounted for, should be random. There should be no discernible large-scale pattern. Instead, the results were astonishing. The AI revealed that in vast regions of the universe, galaxies and quasars were not moving randomly, but were drifting in a coordinated fashion, a coherent flow in a single direction. This wasn't just a local anomaly. The patterns appeared in different parts of the sky, suggesting a phenomenon of immense, perhaps universal scale. This coordinated movement is exactly what you might expect to see if the fabric of space-time itself were gently rotating, dragging everything within it along for the ride. Makarov himself is cautious, acknowledging that such an unexpected result could be due to subtle errors or biases in the observational data. However, the alternative explanation, that the universe as a whole is spinning, is tantalizing. Such a phenomenon is even predicted by some alternative cosmological models, such as the DCDM, Dynamical Dark Energy Cosmological Model, which allows for dynamic changes in the structure of spacetime as it expands.
Interestingly, the idea of a spinning cosmos is not entirely new. It has a surprisingly long and fascinating history, dating back to a contemporary and friend of Albert Einstein, the brilliant Austrian logician Kurt Gödel. In 1949, Gödel, famous for his incompleteness theorems in mathematics, turned his attention to Einstein's equations of general relativity. He discovered a solution that described a universe that was rotating. This wasn't just a mathematical curiosity. Gödel's universe had bizarre properties. Most notably, its rotation so warped the structure of space and time that it would theoretically be possible to travel along a path in a sufficiently large spaceship and arrive back at your starting point before you left, effectively enabling travel into the past. While Einstein admired the mathematical elegance of Gödel's solution, it was largely dismissed as a physically unrealistic model because our own universe didn't appear to be rotating.
For decades, Gödel's rotating universe remained a fringe idea. But then, in the early 2000s, astronomers studying the cosmic microwave background, or CMB, radiation found something strange. The CMB is the afterglow of the Big Bang, the oldest light in the universe, and it fills the entire sky. While incredibly uniform, it has tiny temperature fluctuations, which correspond to the seeds of all future structures like galaxies. According to the Standard Model, these fluctuations should be randomly distributed across the sky. Yet detailed maps from the WMAP satellite revealed that on the very largest scales, the fluctuations were not random. They seemed to be aligned in a preferred direction, an unexpected pattern that cosmologist João Magalhães provocatively dubbed the axis of evil. This name was chosen because the alignment seemed to point in a specific direction relative to our own solar system, and it challenged the fundamental assumption of isotropy. This axis, a subtle alignment in the ancient light of the cosmos, provided the first major observational hint that the universe might indeed have a preferred direction. More recently, other lines of evidence have emerged. Lior Shamir, an astronomer at Kansas State University, analyzed the spin direction of over 200,000 spiral galaxies. Again, if the universe is isotropic, there should be a roughly equal number of galaxies spinning clockwise and counterclockwise. Instead, Shamir found a small but statistically significant imbalance, with a preference for one spin direction over the other. The pattern of this imbalance wasn't random. It formed a quadrupole alignment, consistent with a large-scale rotational motion across the cosmos. Furthermore, some physicists have proposed that a very slow cosmic rotation could resolve one of the most persistent puzzles in modern astronomy, the Hubble tension. This refers to the fact that different methods of measuring the expansion rate of the universe give slightly different answers. Scientists from the University of Hawaii showed that by adding a very slow rotation to their models of the universe, perhaps taking trillions of years for a single turn, they could reconcile these conflicting measurements.
Makarov's discovery, based on the direct motion of over 1 billion galaxies, adds a powerful new piece to this puzzle. It is different from the CMB's axis of evil or the galaxy spin studies, yet it points to a similar conclusion. The universe may not be as uniform and directionless as we have long believed. Of course, extraordinary claims require extraordinary evidence, and the scientific community will rightfully scrutinize these findings. Independent teams will need to verify the results using different methods and future, more powerful telescopes. It is still possible that systematic errors in the data or our analysis methods are creating an illusion of rotation.
However, if further observations confirm that the universe is indeed rotating, the consequences would be profound. It would force a complete reevaluation of the Standard Model of cosmology, the theory that has successfully described the universe's evolution for decades. Fundamental principles would need to be rewritten. The existence of a cosmic axis could have implications for our understanding of dark matter and dark energy, the mysterious components that make up the vast majority of the cosmos. It forces us to reconsider the very nature of space and time on the largest scales. The simple, elegant picture of a universe expanding uniformly in all directions may need to be replaced by a more complex, dynamic, and far more fascinating reality. The cosmos is once again showing us that it is not obliged to fit neatly into our theories, and that its deepest secrets are often hidden in the most subtle of cosmic whispers, waiting for a new generation of tools and minds to finally hear them.